Alright, so I'm going to go over a 2-sample z confidence interval for P1 minus P2. You could also call it a 2-sample z confidence interval for the difference in proportions, or you can just say 2-sample z int for P1 minus P2. Same thing. So here's the problem. Of the 245 random customers who visited a Valley McDonald's this past Saturday, 156 ordered French fries with their meal. So you have basically a McDonald's store, and I'm gonna make it a house. We're gonna call it M for McDonald's, and basically you kind of want to see, the proportion of those who ordered French fries with their meal, but we can't take all the customers who go to this McDonald's, so we take a sample of the customers who go to this McDonald's, and from that sample we take a proportion, right? So we can't get the proportion of the entire, the proportion of all customers in this McDonald's who ordered French fries, because we can't get the capital N. We can't get that sample size. We can't get all of those customers who go to McDonald's. So because we can't calculate P, we instead, take a sample, small sample N, and we calculate, an estimate of that, of the actual proportion of those who ordered French fries with their meal. So this, in this case, we took a random sample of 245 customers, and the point estimate was 156 out of 245, right? Because 156 out of the 245 customers in the sample actually ordered fries with their meal. So 156 divided by 245 is actually 0.6367. So that's your point estimate of the customers who ordered French fries with their meal for McDonald's. Now the next one, a few blocks away, an In-N-Out burger had random. This is not even a sentence. I'm gonna rephrase it. Had 198 random customers, where 110 of them ordered French fries with their meal. So again, I'm going to draw a little house, and I'm going to do I for In-N-Out, and I'm going to take a random sample, small n, and it's going to be a random sample of 198 customers. And from that sample, we're calculating a point estimate, which is the proportion of those customers, of those 198 customers, who ordered French fries with their meal, and only 110 of them did. So 110 divided by 198 is 0.555, I'm just gonna say 6. Okay, so that's what we have so far. And now they're telling us to construct and interpret a 95% confidence interval for the difference in the proportions. So again, we have one proportion here, which is this, and then we have another proportion here. So I'm just going to start by labeling it. So this is going to be N1 because this is sample 1, and then this is going to be N2 because it's sample 2. This is going to be the point estimate 1 because it's the point estimate, or the proportion 1, and we're going to call this point estimate 2. The reason we have a hat here is because it's from a sample, right? It's from a sample. If it was from the entire population of those customers who go to In-N-Out and from the entire population of those customers who go to McDonald's, then it would have just been capital P. But because it's from a sample, we use P hat. Okay? So yeah, we're trying to construct and interpret a 95% confidence interval for the difference in these two proportions, which is P1 minus P2. So this is what we're trying to go for, but we're only going to be able to estimate this using these two proportions. Okay, so when I hear confidence interval, that's going to sound so corny, I panic. So when you hear confidence interval, you want to use panic. So P stands for parameter, A stands for assumptions So basically assumptions that we have to make or conditions that we have to check. And N stands for name of procedure. I stands for actually calculating the interval, so the interval. And then C stands for conclusion. Okay, so we're going to start with P. So the P is the parameter, and so we have to basically take we have to basically define what the two parameters are. So the parameters are basically the things that we're trying to estimate. They're from the population. So P1 is the true proportion of customers in McDonald's who ordered French fries with their meal. And then P2 is the true proportion. Can I just copy this? Proportion, I guess not. The true proportion of customers in, what is it, In-N-Out. I spelled that wrong. In-N-Out who order who order French fries with their meal. So again, these are the parameters that we're trying to estimate. So again, if you remember back in earlier lessons in statistics, you have a population, and anything in a population, any numbers in a population that you want to describe are known as parameters. But because it's really hard to actually find like an actual population size, for example, if you want to get like the true proportion of United States citizens who like flowers, then it's really hard to get all of the United States citizens to get that true proportion. So you take a sample of United States citizens and then you get an estimated proportion, and this estimated proportion is called a statistic. So this statistic estimates the true proportion of those United States citizens who like flowers. So that true proportion is a parameter. So anything that is from a population is a parameter, and then anything that's from a sample is a statistic. So this is P1, parameter 1, and then parameter 2. These are what we're trying to estimate using our statistic that we got from our samples here. Okay, so that's our P. So you always want to make sure to define your parameters. Next is your assumptions. So assumptions, you can also know, think of them as conditions that you have to satisfy. So the first one is that both samples have to be random, and they're usually, it's usually a simple random sample, or it's given to you that it's random. In this case, it's actually given to us. It's saying right over here, of the 245 random customers, and over here, In-N-Out Burger had a random 198 customers. So I'm just going to write that down here. So in your FRQ, you actually want to say, this condition is met for both samples, and then I would actually quote it. I would cite where it says it. So I'm going to say 245 random customers, and then I would say 198 customers, and that would be enough evidence. You don't just want to like write a check mark and then call it a day. You want to say this condition is met for both samples and then kind of have evidence for it. Okay, so that's number one. So, basically these conditions have to be met in order to construct a confidence interval. If they're not met, statisticians, I cannot even say the word people who do statistics, they still want you to proceed with this, or at least, I don't know, but you just say proceed with caution, or like this condition is not met, but proceed with caution. But they're usually always met, especially in an FRQ, because there's no point in doing an FRQ for a confidence interval if the conditions are not met. But maybe they won't be met, and you're just going to have to say proceed with caution and continue with the interval. But anyway, the second condition is the 10% rule. So the 10% rule is basically where n, the sample size, is less than or equal to 0.10 of n. So it's less than or equal to 10% of the population size. So this has to be true for both samples. So it's going to have to end up being like this. So let me just do 1 and 2. So this rule has to be true for both samples. So the sample size for N1 for McDonald's, right, was what? It was 245, less than or equal to 10% of N. In this case, we don't have N, right? We don't have the population size, like the true population size. So because of that, we just take the parameter. Actually, hold on. We don't take the parameter, excuse me. We just write the population. So it's basically all customers who order a meal. Well, obviously customers are going to order a meal because they're customers. So all customers in McDonald's, in that specific McDonald's. And then we say that this is reasonably, did not spell that right. This is reasonably true because obviously 245 is less than 10% of all the customers in McDonald's. And I think that's true because there's usually a lot of customers in McDonald's. And then the second condition, this one over here, is, what was the sample size? What was it, 198? Yeah. So 198 is less than or equal to 0.10 of all customers is it all customers who ordered fries? All customers in and out, right? So all customers in McDonald's, in that McDonald's, and all customers in that in and out. So we're going to say that's also reasonably true. We can't actually solve for it and have like capital N and actually solve for it and be like, oh yeah, it is less than or equal to. We just usually say it's reasonably true. And if it's not reasonably true, you just say condition not met, proceed with caution, and then you continue on. So I'm just going to say condition. Oop, what happened? Okay, condition met. Okay. So then the last one is your normality, or large counts. There's two different names for it. So normality or large counts condition. So basically, this one is where the following has to be met. So your sample size has to be, your sample size times your point estimate or your proportion has to be greater than or equal to 10, and this has to be true for both proportions. So we also have to do for proportion 2. And N1 minus P has to be greater than or equal to 10. And this has to be true for both samples. So, so these conditions have to be true. And these you can actually check because you do have N1 and you do have P1. So let me go ahead and check those. I just want to make sure that I can. Why can't I select? Oh, here it is. This is really bad selecting. That's really bad. This is really, really bad. Actually, I just want to get the bottom. Okay, now I can't move it. This is horrible. It's not moving. How do I get rid of that? Okay, well it's not moving, so I'm gonna have to work with it and do it on the side, I guess. So I'm just gonna work on it on this side, I guess. So we have N1, again, N1 is 245, right? That's the first sample. And what was our proportion? So we calculated our proportion over here. By the way, our equation to find the point estimate, or to find the proportion from a sample size, also known as your point estimate, we'll get there in a second, is P hat is equal to X over N. So it's basically however many, like your sample size, and then however many out of your sample size did whatever. So however many customers in McDonald's who basically ordered fries with their meal. So that's X right there. And so that's what we did. So that's 110. Well, in this case for McDonald's, it's 156 over 245. So that's how we got that. So actually, let me go back and see. It was 0.6367. And then that has to be greater than or equal to 10. And actually, I'll do it right here. So let me find my calculator. Why doesn't it ever show up? Okay, whatever. So what are we doing again? Okay, 245 times 0.6367, and that is 155. 165. Okay, so that's 155. I'm just gonna write that up here, 155.9915, and that's obviously greater than or equal to 10, so that condition is met. And then the second condition is N1, so that's 245, 1 minus 0.6367, so that's 245 times 1 minus 0.6367, and that is 89.0085, which is greater than or equal to 10. So this condition is met. Perfect for the first sample. Now we have to check the same conditions for the second sample. So second sample was what, 198? So the sample size for second sample, right, was 198. And then the actual proportion that we calculated was 0.5556. So 0.5556. And that has to be greater than 10. So 0.5556 times 198 is 110.0088, which is greater than or equal to 10. So that condition is met. And then the next one is 198. 1 minus 0.5556 has to be greater than or equal to 10. So we're going to have to do 198 times 1 minus 0.556, which is 87. That's about 8. 9, 9, 12, which is also greater than or equal to 10. So perfect. All the conditions are met for normality, meaning all the conditions basically are actually met all of them. So it's random, 10% rule, is good for both samples, and normality or large counts is good for both samples too. So now that we have that, what happened? Okay, so we did P, we did A. I'm actually going to change the colors so we can see them. So we did P. We did A. And now we're going to do N. So N, right? N is just the name of the procedure that you're doing. So we already did it over here at the top in the beginning. So it's a 2 sample Z confidence. Oh my god, why? Confidence interval for P1 minus P2. My tablet's acting up now, it's not even writing. Minus P2, or the difference in proportions. So that's the name of the procedure. If you're doing an FRQ, another way you can satisfy this N part is by writing the equation or the formula for the interval with the numbers plugged in, and that I'll show you in a second. So that's all there is for the name part. Then finally we get to the interval part. So your interval, the equation for an interval for two proportions, it always starts the same. It's the point estimate. For any confidence interval, it's always a point estimate plus or minus the margin of error. Now, the margin of error and the point estimate obviously depends on the problem. So the point estimate is whatever statistic. You can think of it as your statistic. Let me zoom in. Maybe that's why the pen isn't working. You can think of it as your, oh yeah, it was. Okay, statistic plus or minus the margin of error. So your point estimate is your statistic. So in this case, what is your statistic? It is actually both P hat 1 and P hat 2. And you want the difference in them, so you're going to write the difference. And that is your point estimate. It's what you're trying to estimate, right? The difference in proportions. That is your statistic. You're actually trying to estimate P1 minus P2, but because you don't have the population information and you only have a sample and you only have the information from there, you only have statistics from there like P hat and N, you can only do this, and this would be your estimate for the population, the true difference in proportions. Okay, so that's your statistic, and then we have plus or minus the margin of error. So your margin of error is actually equal to Z star, we'll get to that in a second, times the standard error of P hat 1 minus P hat 2. Now, let me explain. So, Z star is also known as the critical value. It's just a value that you have to have. It's actually equal to inverse norm in the calculator. Inverse. And it's 1 minus confidence level divided by 2. We'll get to that in a second. Plus or minus. And then standard error is actually... Okay, we'll get to this in a second. So basically, I'll get to Z star in a second, but standard error of the difference in these two proportions, the reason we're calling it standard error is because this is from a sample, and we only call it standard deviation when it's from a population. But because it's from a sample, again, right, terminology, we're calling it standard error of P hat 1 minus P hat 2, or the difference in those proportions. And that standard error is actually equal to P hat 1 times 1 minus P hat 1 divided by N1 plus p hat 2, 1 minus p hat 2 divided by n2. Yeah, that's it. You're just gonna have to memorize that. Anyway, so this is what we have so far. Now, inverse norm is a function in your calculator, and I'm going to show you how to get that. And then this CL. CL is your confidence level. Confidence. And you get this in the problem because it tells you what type, how confident your interval, they want your interval to be. And they're telling you they want a 95% confident interval. So 95% is your confidence level. And actually, when you're plugging it into the equation, you're going to put it as an actual proportion, which is 0.95. So your confidence level is going to be 0.95. So it's going to be 0.95, 1 minus that divided by 2, and then inverse norm. And then we're going to plug in these numbers also. So we already know that N1 is 245, this is 198, right? Let me not be wrong. Hold up. Let me check the answer. 245, right? Yeah, 245, 198. P hat 1, I think it's 0.6367, I think. Hopefully. Let me just delete this and do this one first because it's too long. Then it's 1 minus 0.6367. Let me just double check that that is right. It's 0.6367, yes. And then P hat 2 is 0.5556, 1 minus 0.5556. And then you're dividing by 198. That is your standard error for P hat 1 minus P hat 2. And then we're going to plug in P hat 1, which is 0.6367 minus 0.5556, right? And then this over here should give us something around 0.0811, right? The point estimate, plus or minus, we're going to get to this part, I'm going to leave that there. And then times this number over here, which should give us a big number, 70, 49359. You could round if you want, but I don't like rounding until the end. So that's what we get so far, and now we're going to solve for this. I'm going to show you how to do that. So if you have a TI-83, you have this function, but for like hypothesis tests, for like t-tests, you won't have that. So TI-84s are the way to go, but you can do this with a TI-83. Now, if you, okay, so I don't know, because I don't have a calculator here. So I don't have an online calculator, but I'll just show you the steps. I guess I'll write the steps for you. So for this one, I guess I'll just do this to the side. To calculate inverse norm, or to find Z star, you want to go to second. Let me bring out my calculator. I think it's second bars and then 3. But let me see if I can take out my calculator and see what it actually is. Okay, here it is. Okay, second bars, or second distribution, whatever you want to call it. I like to call it vars. Second vars, 3. Which is inverse norm, and then you just put in, it's going to give you, it's going to return inverse norm, and then you just plug in those values. You just do 1 minus 0.95 divided by 2, and let me actually do that, 1.95. So second vars 3, parenthesis, 1 minus 0.95, parenthesis, divide by 2, and parenthesis. And it should give you actually a negative 1.95, but here's the thing. We always want to take the absolute value of it. Just go with me on that and trust me. We always take the absolute value of it. And yeah, so that's pretty much it. So, and we always round to the 100th place, I think. Yeah, we don't round to the 10th, right? We round 2 decimal places, so 100th place. So it's going to be 1.96, and we're going to take that. So that's what it should give you. Well, that's not what it should give you. It gave you negative 1.9599, whatever, but this is the actual answer. So that is that. Now we have that. Another way really quickly that you can actually do this is with Python. So let me show you that real quick. A little extension here. Hold on. No, let me go here. Data. Oh, no. Deep notes. I don't think I had day 201. This is one proportion. I need a difference in proportion. No. Oh yeah, right here. Okay. Oh no, that's a T-stop. Never mind. Confidence interval, blah, blah, blah. I know for sure that I wrote a function like this. Hold on, let me find it. I don't think they told us to write a difference in proportions. No. By that time we were doing means. Yeah, that's not what we're doing. Okay. I guess we could just write it now, I guess. So, basically, just go to Deep Notes, right? Just Google Deep Notes and just make a Python notebook and then just copy and paste this and it will work. But this is only for a 1 sample interval, so I have to actually fix this and edit it to be a 2 samples. So, actually, this is a function that'll give you the entire interval, but really the only thing to get Z star is this. It's always going to be the same, whether it's going to be a 2 sample interval or a, what do you call it? A 1 sample interval. So CL, your confidence level is 0.95, right? And if I just run this, it should give me the same, it was Z star. Hold on. Let me run it. It's gonna take a little while. Okay. Norm is not defined. Okay, let me just copy and paste these libraries and just paste that over here because I forgot, and now run it again. And I didn't even print Z star, so now let me print Z star and run it again. Okay, 1.96. See? So just copy and paste this, man. If you don't have a TI, actually, a TI-83 should have this function because I have a TI-83. But if you just don't have your calculator with you and you're on the go, just copy this into a Python IDE. You can literally, no, never mind. Yeah, you can use Google Collaboratory or you can use Deep Notes. Copy this and it'll just change your confidence level and it will give you the Z star for that you need. So 1.96. So that's another way to do that. I also have this function here that's actually going to give you the whole confidence interval given like a certain like 0.95. But this is for a 1 sample, so I'll have to edit it for a 2 sample, but yeah. Ignore this. Focus on this. Okay, moving on, back to the problem. That was just a little shortcut just in case. I spent days trying to figure that out because I actually didn't have a TI-84, so I just kind of made my own functions to do my problems for me because I was not about to do all of that by hand. Like, it's so tedious. Anyway, yeah. So this is what we have so far. So I then multiplied 1.96 and then this big number. So basically the Z star times the standard error P hat 1 minus P hat 2. And that didn't even, right? I basically multiplied those numbers together. And I got 0.811 plus or minus. Here we go, let me zoom in. 0, really? 0.0811 plus or minus, again, this big number, 70216,744, and then you take this number, which is your point estimate, and then you subtract it. You subtract this number from your point estimate, and you get your first endpoint, which is this is 0.74, negative 0.0106, and then you take this number and you add it to your point estimate, and you get your second endpoint, which is 0.1728, right? And that is your confidence interval. So now, what does this mean? How do we conclude this? So this is where C comes in. Yay, we're finally almost done. Okay, let me go here. So our C stands for conclusion. So basically, we say we are blank. So that's going to be your percentage, they're your confidence level. So 95% confident that the interval from negative 0.0106 to 0.1728 captures the true, really important, the true difference in proportions between customers who go to McDonald's and In-N-Out and order fries with their meal. Beautiful. So captures the true difference in proportion between fries. So that's the context. Okay, so let me kind of give you a little template. So this is your confidence level, so how confident you are. So we are 95% confident that this interval, right? So that's the second part. So this is the interval, right? You get from here. So that's the interval. And then finally, you have the true difference in proportion, which is kind of your parameter that you're trying to find. So this is your parameter. And then you also have your context, right? So this is your context. This is your context, and then this is your context. Okay, so that's your conclusion, that's a template for it, and that's what you want to write, and that's it. That's all there is to it. Yep, pretty much all there is to it. And yeah, that's this whole thing right here. That's a lot. But yeah, so the true difference in proportions between those customers who go to McDonald's and In-N-Out and order fries along with their meals is, well, we are 95% confident that that thing, the true difference in proportions of that context lies within that interval. So it's going to be in that interval. Well, we're 95% confident at least, right? So yeah, that's the answer. Okay, so you can stop watching the video here, but I actually wanted to see if I could really quickly modify this function to be confidence interval for two proportions. for the difference, for difference in two proportions. Okay. I'm gonna try to see if I could do that, but you could stop watching the video now. Like, the answer is the answer, but this is just like, it's gonna give you, it's a way you can check your answer, you know. It's gonna just literally give you the confidence interval. And yeah, so n2, right, and we have also x2, and then we have our confidence level, so we don't need to change that. So then I'm going to do p hat, I'm going to call this p hat 1, and then do p hat 2. We just have to basically double everything. P hat 2 instead of equal to x2 over n2, and this is x over n1. Okay, and then just so we're clear, let me just do n1, x1, so everything makes sense. Standard error of p hat 1 minus p hat 2 is equal to the square root of p hat 1 minus p hat 1, right? So let me take that, and that's 1, right? Actually, this whole thing is 1. So I'm going to put in parentheses. And this is n1, and then we're just adding it with another thing here. And this is n2. This is going to be n2. N2. That's a 0, not a 2. And then we're going to round it to 4 decimal places. And then this is z star, so we don't really have to do anything there. Margin of error is z star times this, right? I already defined it up there. And then n.2 is p hat 1, right? Minus, actually, hold on. I have a point estimate. Yeah, it's actually p hat 1 minus p hat 2. That's your point estimate. So it's not necessarily p hat anymore, in this case at least. So just add that there, plus margin of error, okay, blah blah blah. And n.2 confidence interval, so it's, what did I do? Okay. So we do have a 0.95 confidence level, so our n1 was 245, our n2 was 198, our x1 was, I don't remember, so let's go and see what it was. We go back up in our problem. Oh, come on, what did I do? So our x1 was 156. Ugh. I don't like this new update. It's so weird. Let me just put it smaller. Okay, so our x1 is 156. And then our x2 is 110. No, not 1,120. And then our confidence level is 0.92. And if we run that, we should get, nope. Okay, sorry, I forgot that. Forgot I renamed the function. Copy, paste it. Okay, we should get something. I guess not. Oh my god. Okay, what? Line 14. Where is line 14? Oh, okay, should put it outside of the function. Outside. What now? Confidence level. It's right there. Oh, I forgot to put a comma. Okay, now can we please be good? 0.0105, okay, let me not round then. Let me just leave it as it is, and then you'll see that it is the actual, actually it is the answer. It's obviously the answer. But let me just not round, and then you'll see the full answer, and making a decision of your own. Okay, see? So we got that, right? And it's similar to our answer, because I rounded, I don't know why. whatever, it's the same thing. It's just one decimal place. What did I do now? Oh, I forgot to. Okay, there we go. Okay, so if we go all the way back down, just to double check our answer, let's go. Where's our answer? Oh, right here. This is our confidence interval, right? Negative 0. Blah 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 blah. Okay, yeah, same thing. Negative 0.0105, except minus 0.106. Not really much of a difference. I just rounded differently. And then I got, for the second endpoint, is 0.1729, and I just did 0.1728. So I guess I rounded differently. But as you can see, this is the confidence interval for a difference in two proportions. If you want to just double check your answer and you don't have your calculator with you to calculate Z star, then you can just copy and paste this into Google Collaboratory or a Deep Notes notebook, which is where I am at right now, and just plug in your data, right? So your N1, your N2, your X1, your X2, your CL, which should all be given to you, and then just run it and it should give you your confidence interval. So that's a quick shortcut. I spent days working on how to figure this out, and it was so worth it. I'm so thankful that God allowed me to. Literally, this is the part. Literally, this was the hardest thing of my life. Like, it was so hard to find this function. I don't know why. I don't know why. It was just so hard, but I did it. We did it, guys. So yeah, I'm really proud of this. And really thankful. So that's that. So that's a shortcut. Anything else that I want to show you? Not really. Okay. Oh, don't tell me that I had it. Oh, I had it for a T interval for mean difference. I didn't have... Yeah, that's different. Okay. Anyway, that's that. I'm going to end the video now because girl has like 4 other confidence intervals to do because I have a test tomorrow. So, bye.